All right, let's dive right into one of the strangest, most mind-bending ideas in all of science, quantum entanglement. Get ready, because we're about to find out that the universe is, well, it's a whole lot weirder than you probably think.
You know, this whole mystery really kicks off with a complaint from Albert Einstein, of all people. When he first heard about entanglement, he famously called it spooky action at a distance. He just thought it was so absurd, so completely against the rules of the universe, that it simply couldn't be true.
So that's the real question, isn't it? What could possibly be so weird that it stumped one of the greatest scientific minds ever? Well, that's what we're going to unpack. We're going to dig into that spooky action and see why it makes us question everything we think we know about reality.
Okay, so to really get what bothered Einstein so much, we have to start with something we all take for granted: our own common sense. See, we all walk around with this built-in set of rules for how the world is supposed to work, and we don't even realize it. It all boils down to two really simple ideas: realism and locality.
Let's try a little thought experiment. Imagine you have two quarters, one from 1999, one from 2000. You shake them up in your hands and hold one in each closed fist. Okay, rule number one is realism. It just says that the quarter in your left hand has a definite date, right now, even though you can't see it. The date is a real property it already has. Peeking at it just reveals that property. Make sense? Rule number two is locality. This is even more obvious. Opening your left hand to see the 1999 quarter can't magically change the date of the quarter in your right hand. An action here doesn't instantly affect something over there.
I mean, those two ideas seem ridiculously obvious, right? They're basically the rules we live by every single day. And when you put them together, you get this really powerful, official assumption about how the universe ought to work.
And that whole common sense package deal has a name: local realism. It's the bedrock of our intuition. It says objects have definite properties, whether we're looking or not, and you can't instantly affect something far away just by fiddling with something here. This was Einstein's worldview.
So, Einstein looked at quantum mechanics, which is all about probabilities and maybes, and he said, nope, this can't be the whole story. It's incomplete. He was sure there had to be some hidden variables, some secret instructions that determine everything perfectly. We just can't see them yet. It's kind of like a computer program spitting out what looks like random numbers. Now, you could just say, well, I guess it's random, but the complete theory would be knowing the hidden code inside, like the computer's internal clock that's actually dictating every single number.
But then, quantum entanglement walks onto the stage, and it looks at our entire common sense picture of the world and basically just tears it to shreds. It's the universe itself telling us, yeah, about your rules, they don't apply down here.
So what in the world are entangled particles? Imagine two particles, like cosmic twins, born at the same moment and mysteriously linked. No matter how far apart you take them, across a lab or across the galaxy, what happens to one instantly affects the other. And here's the truly spooky part. Quantum theory says their properties, like their spin, aren't just unknown before you look. They are literally undetermined. They don't exist yet. The very act of measuring one twin forces the other one, wherever it is, to snap into a definite state, instantly.
Now, for decades, this was just an argument for philosophers. You had Einstein saying hidden variables, and his rival Niels Bohr saying, nope, the universe is just that weird. But then, in 1964, a physicist named John Bell came up with an absolutely ingenious way to finally test it. He figured out how to put common sense itself on trial.
And Bell's brilliant idea can be framed as a simple game. We can call it, do the lights match the buttons? The whole point is to see if any strategy based on our common sense rules, local realism, can explain what actually happens in the quantum world.
Okay, here's how it works. You have Alice and Bob in separate rooms, each with one of those entangled twin particles. They each have a detector with two buttons, green and red, and two lights, green and red. For every particle, they each randomly press a button, and a light flashes. Now, the scoring is key. If they happen to press the same colored button, they get a point if their lights match. Same for red and red. If they press different colored buttons, they still get a point if the lights match, with one crucial exception. If Alice presses green and Bob presses red, they only score if their lights are different.
Now listen closely, because this is the absolute core of it. Bell proved mathematically that if those particles are playing by our common sense rules, if they have some pre-programmed instructions and can't communicate, then there is a hard, unbreakable limit to how often they can win this game. No matter what secret strategy they might have,
The absolute best they can possibly score is 75% of the time.
So, what happens when scientists actually run this experiment with real entangled particles? They win, about 85% of the time. They don't just break the limit, they completely shatter it. They consistently pull off a score that should be absolutely impossible.
And look, this isn't a fluke. This experiment has been done countless times with incredible precision, and the result is always the same. And the conclusion it forces on us, well, it's just staggering.
Here it is, side by side. The conflict couldn't be clearer. Our common sense view of the world predicts a score of 75% or less. The actual quantum universe delivers a score of around 85%. These two things cannot both be true. The numbers just don't lie.
So, the verdict is in. Local realism is wrong. That foundational, common-sense assumption we all carry around about how reality should work, it's just not how the universe operates at its deepest level. Experiment has proven our intuition wrong.
So if local realism is wrong, we're left with some really strange choices. It means at least one of our bedrock beliefs about the universe has to go. Either realism is false, meaning a particle's properties literally don't exist until we measure them, or locality is false, meaning Einstein's spooky action at a distance is totally real, and particles can influence each other instantly across the cosmos. Or, of course, both could be false.
Yeah, none of those options are exactly comfortable, are they? They all paint a picture of a universe that's deeply interconnected and just plain bizarre in a way that completely defies our day-to-day experience. This isn't just a clever puzzle anymore. It's a deep truth about what it means to exist.
So what's the big takeaway from all this? It's that the universe, at its most fundamental level, doesn't play by the rules we expect it to. And answering Einstein's question about whether quantum mechanics was complete, we didn't find a nice, neat final answer. Instead, we just opened the door to a much deeper, more profound mystery about what reality even is.
Which leaves us with a final thought to chew on. Are we, when we make these measurements, just getting these fleeting glimpses of a true reality that's forever hidden from us? Or, and this is the really wild part, is the very act of looking what helps create the reality we see? Quantum entanglement doesn't give us the answer, but it forces us, brilliantly and spookily, to finally ask the question,